So in this problem, we're given a situation that looks like this. We have a tire of mass little m and radius little r that has moment of inertia I equals 3/4 mr squared. The tire lies at the top of a slope of height h, and at the end of the slope, we have a semicircular arc that starts at point A up here, has radius r, and we're told that at some angle theta within that arc, the tire is going to leave the surface of the slope. Now, in order to figure out where that angle is, we're going to draw a little isolation diagram for the tire. We have the force of gravity pulling it down, normal force pushing it away from the surface, and the force of friction, which since it's rolling is not going to do very much. Also, because we're only really worried about the radial force, since we're dealing with circular motion, the force of friction isn't really going to play into our calculations at all. So we know that the normal force points perpendicular to the surface, which means it's going to point along this angle theta. So this tells us that the normal force makes an angle theta with the vertical. And since mg is pointing vertically downwards, we know that there's also an angle theta here. This tells us that the radial component of mg is equal to mg cosine theta, and the total radial component of the force is mg cosine theta minus n. Now, at all points where the tire is maintaining circular motion, this is going to have to be equal to mv squared over r. And at the point where the tire is just about to leave the surface of the slope, the normal force is going to drop to 0, and we're going to get just mg cosine theta equals mv squared over r, where g cosine theta equals v squared over r. So now all we have to do is solve for v squared. That's a pretty simple energy calculation. All we need to do is note that energy is conserved, since the friction force does not do any work upon the tire, since all it does is keep it rolling without slipping. And so energy is conserved. The initial energy is just gravitational potential energy, which is going to be mgh, since it starts out not moving. The final energy at this point theta, or at this point at an angle theta, we're going to have gravitational potential energy, mgr cosine theta, since it's still at some height above the ground. And then we're going to have translational kinetic energy, 1 over 2 mv squared, and rotational kinetic energy, 1 over 2 I omega squared. Now we know that I is 3 over 4 mr squared, so we're going to have an r squared term in here, and we know that r times omega is equal to v. So that tells us that this is actually just 3/8 mv squared. So we can add that in. We get mg r cosine theta plus 3/8 plus 4/8 is 1/2, gives us 7/8 mv squared for our final, our total final energy. So now we can use these two equations, set them equal to each other, and solve for v squared. We get 7/8 mv squared equals mg times h minus r cosine theta. The m's are going to cancel out, and we get v squared is equal to 8g over 7 times h minus r cosine theta. Now plugging that in over here, we get g cosine theta is equal to 8g over 7r times h minus r cosine theta. We can cancel out the g's, and now we have this term of 8 over 7r times r cosine theta is just 8 cosine theta over 7. And we're going to pull this over to the left. We get 1 plus 8 over 7 is going to be 15 over 7. So we get cosine theta times 15 over 7 is equal to 8h over 7r. And so now, multiplying through by 7 over 15 to isolate cosine theta, we get cosine theta is equal to 8h over 15r, and theta is equal to arc cosine of 8h over 15r. Now in part B, we're asked at what point this formula is going to stop being valid. And so it's only going to stop being valid when the domain no longer makes sense. So we know that cosine reaches a maximum of 1. And so what that means is that as h increases, at some point this term 8h over 15r is going to go beyond 1, which means that the arc cosine of that term is no longer going to be defined. So at that point, this formula will cease to hold, and what that'll mean is that the tire will be moving fast enough by the time it reaches the point A that it won't reach any angle theta at all. It'll just immediately leave the track at point A. Theta will be 0, but theta will be 0 no matter how much higher h goes beyond that. So h could be, for instance, h could be 15r over 8, and it would leave the track at point A, or h could be 30r, and it would leave the track at point A. No matter how much higher the tire starts, it'll always leave the track at that